So on your screens, you should see a recording to the cloud. And let me share my screen with you. And just want to verify that you can hear me and you can see my screen.
Yes.
Yes, awesome. All right, so I'm just going to add a page there and start with that. All right, so I am going to begin with derivatives of logarithms. And so they begin with a couple of conjectures for you to remember. They give you, starting with the derivative of some logarithm of some base a, x, and that is going to be equal to 1 over the natural log of that base a times x. And so we'll do a few examples of that in a few minutes. And second one that I want to share with you is also that if you have a derivative of some value natural log x, the derivative is always going to be something similar to 1 over x, and that's the easiest way to remember it. So I can share with you a couple of examples. I'm going to share with you this one. For example, if I have a function, and this is just a random example, and that function is equal to some natural log of 15x. What happens is basically when you look at this is the derivative of the g of x over g of x. And if I look at this, in addition to that, like this would be 15 over 15x. And so if you notice, the 15s are going to cancel, and you're going to end up with 1 over x for an answer. So this is the idea of how we arrived there. So just keep that in mind. So let me give you example 1 in the textbook. And so they ask us to find the derivative and then they give us y equals log of x. And I want you to go back to your foundation concepts. I want you to remember that there's a little base 10 here we don't talk about very often. And so the base is part of this calculation for the derivative. So we take dy over dx, and this is going to be equal to 1 over the natural log of the base, which in our case is 10x. So all of this comes from the base itself. And that's the first example I shared with you. If you look carefully here. And so that goes with that example. Okay. Second example I have for you here. We'll call it example. This is example A. I'm going to give you example B, where I have y equals 7 natural log of some variable t. So in this case, I want you to remember that this is 7 times the derivative of that natural log of t. And so that becomes the derivative 7 times 1 over t. And my final answer here will be simply 7 over t. So that's fairly easy, yes?
Yes.
Example 2. And this one, I'm looking to find the derivative of the function. I'm not going to write the derivative every time. So I just want you to know that if I say this, I'm saying, you know, you're going to find the derivative of, and they're giving us the function f of x is equal to the natural log of 6x. So I want you to remember in this case that again, the first derivative is simply going to be the derivative of the 6x over g of x. And so in this case, this will become 6 over 6x. One more time, just to remind you, the 6's will cancel, and you're left with your answer, 1 over x. Is that fair? Easy to remember?
So far it is.
So far, so
Yes.
good? You know what I say, run with it. All right, so let's look at this as if it were example A. So example B, in this case, we have been given the natural log of an expression x squared plus 1. Okay, so I want you to remember that this also has a g of x. And so if you think of the g first derivative of g of x, we're going to get 2x. And the original function, well, that doesn't change. That's your x squared plus 1. And so the rule of thumb is right here. So your final answer here will be simply 2x over x squared plus 1. And if you graph this, this will make a lot of sense. You'll see the connection and why you see the slope and change, rate of change happen at that point. So the third example of the same type is y equals log base 2 of 3x squared minus 4x. And so, long story short, our derivative would simply be 6x minus 4, correct? That is divided by the natural log of 2. So you have to account for the base. And this will be 3x squared minus 4x, simply repeated at the bottom. So all of that is your derivative for that particular function. I also want to make a note, and this is something for you to take home with you. And I want you to keep in mind that if I'm looking at the derivative of the function where y equals the natural log of negative x, for example, where the x value is less than 0, we're going to employ the chain rule. We employ the chain rule. And so if I look at this as a chain, we end up with a g of x. Well, that's equivalent to our negative x. And our first derivative for that will simply be negative 1. And so if you think of this, basically we have the derivative which is our derivative function over g of x. And this is equivalent to negative 1 over negative x, which is simply 1 over x. Okay, and that's kind of like you need to know this kind of situation. Okay, so here are some more derivatives that I want to talk to you about. We can have a derivative of the log. So if I have the derivative d over dx, and they're giving me the log, so let's say this is the log of base a absolute value of x our derivative notation would be 1 over the natural log of a of x. Just like you see it. There's 4 of these, so I'll call this A. If I look at B, what if I have the derivative? So let's do the derivative d over dx. And this time I'm looking at the natural log of the absolute value of x. Well, this is simply going to be 1 over x. And this is one of those, it is what it is. It's like a function notation we use. D over dx, if we're looking at this in terms of log base a, if I have a function here, let's call it absolute value of g of x, then I'm going to re-express this as 1 over natural log of a, and this is times g prime x, the first derivative, over g of x. And I think I showed you a prior example of that already. And in D, part D, I have, if I'm looking at the derivative of the natural log of g of x, then this is equivalent to my first derivative of g of x over g of x itself. So let me show you example 3, which kind of brings this home. And pay in particular attention to B as one example here that might help you put it together, so to speak.
Is that the absolute value of the function g of x in B? Okay.
Okay, I'm going to go ahead and refer to this as example 3. And in this example, I have, again, a function given to me as y equals natural log absolute value 5x. And so I want you to remember that if I take the derivative of 5x, I get 5. And the original function, which is basically 5x. So again, 5 over 5x reduces to 1 over x. And so that's just, like I said, in a prior example, it's one of those patterned behaviors of the derivative when it comes to logarithms. Here comes B. In B, I'm asking you to find the first derivative if I give you the function f of x, and I say to you that is equal to 3x natural log of x squared. So again, this is actually basically going to be our product, right? So we're going to use product rule. So if I have, let me take you back to product rule if you don't remember. So just to remind you, in product rule, let's say we have u of x times the derivative of the v of x plus the v of x function times the derivative of the u of x function. And so if I look at 3x as my u of x, I know my derivative of that is simply going to be 3. If my v of x function, well, that's the natural log of x squared. The derivative of that natural log x squared is simply going to be the 2x over x squared. And so I could collapse this further. If I multiply this out, this is going to give me 6x squared over x squared. And this is plus, this is going to be 3 natural log of x squared, right? And if I simplify the x squares, my final answer, or my first derivative, in this case, is simply going to be 6 plus 3 natural log of x squared. Are you okay with that one?
Yeah, I feel okay.
Oh, I forgot one little thing here. I just realized that this is, if I use power rule, this will actually end up becoming natural log x squared raised to the third power. So actually this will simplify further, where this 3 and this 2 become 6. I forgot to mention that step. And at this point, just remember this is called, we call this power rule for this one. This is basically power rule. So if we use power rule, that simplifies down to that. All right. Let's see. I have another example. This is example C. And like I said, I'm going to give you a nice little mix of questions so we can just go over the questions before I begin trigonometry, derivatives of trigonometry. So we begin with our function where I have s of t is equivalent to log base 8 of t plus 1, and this is over t. So immediately I'm thinking quotient rule. Now this one you need to be careful because the order in which we do things does matter. And so if I think of all of this as u of x at the top, and this is over v of x. So I want you to start to set up the question where we're focusing on u of x and its derivative. So u of x, we know, is going to be the log base 8 of t plus 1. And we know that the derivative of u of x, well, that's going to be, first of all, 1 over the natural log of 8. And again, that goes back to what I showed you earlier. Times, this is going to be 1 over t plus 1. And then times 1. All right. So the v of x, well, that's simple because that's v of x is simply t. And we know that that first derivative of x is simply 1. So if we throw this into the quotient rule, I'm going to do that right here. I'm going to say, well, that first derivative using a quotient rule is equal to that t times 1 over natural log of 8 times 1 over of t plus 1 times 1 minus, and then this becomes log of 8 t plus 1 times 1. Remember, this is part of the original question. All of this over t squared, that's your v of t. So we can now multiply. If I take out natural log of t plus 1, and I multiply that top and bottom. Let me do it this way so we don't get confused. I'm going to come over here and I'm going to multiply this by 8 natural log of 8 times t plus 1 top and bottom. So this will be natural log of 8 as well, times t plus 1. And so when this reduces, or we multiply this out, this reduces down to t minus the natural log of 8 times t plus 1 log base 8 t plus 1. And this will be all over t squared times t plus 1. So this will be natural log of 8. Because all we're doing is multiplying it across, and that's how we end up there. And so,
Excuse me.
uh-huh.
I'm just wondering why is that in I was writing my notes, but why is that in red ink versus the black ink?
It doesn't really matter. At this point, what I did was in the red ink, this part is just to remind you that we're multiplying by that. And so
Okay.
the end result is in red as well. If you want to change the color, I will.
No, that's not it. I was just looking down at my notes. I was wondering if is that the next part of the black? Did the black turn into that?
So this, after you multiply here, after you multiply that, that's one part. This is the end result.
All right.
Okay. That was a doozy. I'm going to give you a bunch of these in a few minutes, so just hang tight. We'll have plenty of time to practice. Okay, I'm going to do example 4. So in example 4, we're still dealing with we're still dealing with finding the derivative of functions, and this one is the only thing that changes here is now we have a base e and an x squared. So they're giving us, in example 4, we're going to find the derivative of f of x equal to the natural log of x squared e squared, or I'm sorry, e to the x. My apologies. I misread that. Okay, and so in doing this, remember that we're multiplying two bases in this case. So we're going to rewrite this. So I want you to think of a rewrite where now I'm going to look at this as two functions where I have natural log of x squared plus the natural log of e to the x. Think of that as step 1. If I employ the power rule, this will now become 2 natural log x plus x natural log e. Now there's a little secret in math in terms of natural log. I want you to remember that natural log and base e kind of zap each other out. And so this function, if you think of it that way, it now becomes 2 natural log x plus x. Now, if I look at the first derivative, this is now really just simply first derivative is now equal to 2 over x plus 1. And that will be your last step right here. Okay, you do remember that natural log of x, if you're taking the derivative of some natural log x, your answer in the first derivative notation is going to be 1 over x, right? Keep that in mind. Just remember that. All right. Are we okay so far? Hanging in there?
Yep.
Yes.
Okay. Some of this is new, some of this probably not so new. Okay, let me look at the notes for the next piece. In the next piece, you have another natural log. So this is still example 4. They're giving us g of x, and that is equal to the natural log of x plus 1 over x minus 1 squared. So again, I'm thinking of this in terms of what we learned with respect to dividing the same base, right? So in this case, we end up with g of x, or re-expressing this as g of x is equal to the natural log of x plus 1 minus the natural log of x minus 1 squared. Or cubed, I'm sorry, this is cubed. So far, you understand this part, right? And now the next step, if we use power rule, we have natural log of x plus 1, and this is really taking it step by step. This is minus 3 natural log of x minus 1. That's using the power rule. And now we express the derivative equivalent. So the derivative of the natural log of x plus 1 is 1 over x plus 1 minus 3 times 1 over x minus 1. Okay, and so this gives us, obviously, if we condense it, this will give us 1 over x plus 1 minus 3 over x minus 1. But now we want the same denominator. So we have an x plus 1 and an x minus 1. So I'm going to multiply this top part by x minus 1. And I'm going to multiply this top part by x plus 1. And now, doing a little bit of algebra, you can see that we end up with x plus 1 and minus 3x minus 3, which gives us negative 2x minus 4 and over the combined denominator of x plus 1 times x minus 1. Make sense? Okay, we're going to hit the trigonometry next. And I want to, before I do that, let me give you some sample questions. Let's do some practice. And so I'm going to throw some questions out. I'm going to ask you if you would respond back and tell me what you think. So I want you to find the derivative of each. That is basically the next 9 or 10 questions. This is what we're going to focus on. We're going to find that derivative. I'm going to start you with question number 1. So for practice, if f of x is the function given to you, and that is equal to the natural log of 3x, would you find the derivative? What do you think it's going to be?
Is it 1 over x?
It's 1 over x, yes. Because if you remember, this is basically going to become the first derivative of the 3x over the g of x. If you do the math, this becomes 3 over 3x, and this will cancel, or reduce, I should say, and becomes 1 over x. Okay, second challenge question before I begin trigonometry questions. Find the first derivative if I'm giving you that function f of x, call it whatever you want to call it, it's equal to the natural log of 8 minus 3x. What do you think that derivative is going to be? Remember, it's still a natural log. Okay, so what would you consider the g of x to be? Don't be shy, it's just 8 minus 3x, right? So what is the first derivative of this function?
3.
-3, right? So according to the method I showed you, this is going to be -3 over 8 minus 3x. That's the first derivative of that function. Let me give you another one. This is a 2a, so we're still on the same concept. What if I asked you, find for me the derivative, if I'm telling you the derivative of the function is natural log of 5 minus 6x. What's the first derivative?
Would it be -6 over 5 minus 6x?
-6 over 5 minus 6x. Winner, winner, chicken dinner. Very good. Did you get it? So basically our g of x in our example is simply the 5 minus 6x. Okay, if you want to highlight it just to remind you, it's that. That's their first derivative. And what we want to do now, or our function, our first derivative of that function was simply using differentiation would be 6x, -6, right? So it's always the g prime x over the g of x. Is it sinking?
Yes, it is.
It's sinking in. Good. Very similar concept. Question 3. What if I said to you I have y equals the natural log of the absolute value of 5n squared, excuse me, 5x squared. I don't know where I got the n from. My bad handwriting is where I got that from. 5x squared minus 7x. Very similar concept. Okay, first of all, my function g of x, forget about the absolute value signs. It's simply 5x squared minus 7x. Done. Using differentiation, what is this first derivative?
10x minus 7.
10x minus 7. So our first derivative for our equation is 10x minus 7 over 5x squared minus 7x. Not too bad, right? Are you feeling this? Look, try this one if you're not feeling it for size. I have the natural log of the absolute value of 3x squared minus 5x. What is the first derivative?
6x minus 5.
Yeah, their first derivative will be 6x minus 5 over. You gotta finish the bottom part. 3x squared minus 5x. That's it. Remember, it's always this for, let me use the other example. The first derivative of the function itself. So when I say the function, I'm relating here. And so the first derivative of this function, g of x, which is the original 3x squared minus 5x, I'm simply asking you to find the first derivative, which is 6x minus 5. You remember when we did that, when we began, and I said to you, multiply 3 times 2, and here multiply 1 times 5, and now we take away 1, take away 1. And that's how you end up with 6x minus 5 in this case. Are you okay with these? Are you feeling them, seeing them at least?
Hmm.
Yes, no, maybe?
Yes.
Okay. Well, worst case scenario, you can always look back again, and when you hit the Pearson, I know that I left the function of you an example so you can follow me. Okay, so I'm gonna ask you for the first derivative. I said to you y equals natural log of the square root of x plus 18.
This
This
be the same. We're sorry. Is this be the same case where we forget about that that symbol?
This gets a little weirder because you have the square root. Remember the power rule and the square root thing? So look at what's going to happen here.
1/2.
Yeah, you have to do 1/2. So this will become basically a chain rule kind of situation because you have x plus 18. And this is this to the 1/2 power. So I have to multiply, and that's going to become 1/2. And then this is going to take away 1, because remember, I'm taking away 1, I'm really taking away 2/2. So 1 minus 2 is minus 1/2. So what's going to happen is I need to correct that. So this becomes 1/x plus 18 to the positive 1/2, which becomes 1/the square root of x plus 18. So depending on what they expect of you, I think either one of these two answers might be okay. Depends on the question, okay? Let's do another one to practice this concept. I'll leave that up here, and I'll give you a minute. Try 4B. I'm going to give you where y equals the natural log of the square root of x plus 8. Let's see what we get here.
You get 1 over the square root of x plus 8.
Are we missing something?
No, I was just wondering if that was the answer.
You came doggone close. You said 1/, or 1/, something else square x plus 8.
Yeah, I was wondering if the answer is 1 over the square root of x plus 8 because the previous answer was 1 over the square root of what was next to the natural log. So I was wondering if it was the exact same.
Well, remember, you're very close. This is the natural log of x plus 8 raised to the 1/2 power. There's one little detail missing.
All right.
Remember, you're going to multiply by 1/2, so it's 1/2. And then this becomes square root x plus 8. And same process, right? Because we're going to take the x plus 8. You're going to multiply it by 1/2. So it's 1/2 times this, and this becomes x plus 8 to the 1/2 minus 1, which is the negative 1/2. So you have to correct it and bring it down below the fraction bar. So it becomes positive. So it'll be 1/2 square root x plus 8. I have a couple others to practice, so let's do 2 more or 3 more. All right, let's try this one. What if I give you, let's call this 4C. And I'm going to ask you to find the first derivative, that's what we're doing for all of these, of the natural log of the square root of x plus 13. What do you think this is going to be?
Is it 1 over
1
Two.
over
square root x plus 13?
1 over 2 square root of x plus 13. Very good. All right. You feel okay with this?
Mhm.
Okay, you'll see plenty of these in my math lab. All right, so let's try this example 5, we'll call it 5a. I have a function, some function f of x, and I'm going to call this negative 3x natural log of 4x plus 3. Can you tell me its first derivative? Okay, so on this one, you remember the product rule again. Where I need a u of x, I'm going to multiply that times the first derivative of the v of x plus the v of x, and that times the first derivative of the u of x. Okay. So in this example, my u of x is going to be the negative 3x. My u of x derivative is going to be negative 3. Do we agree?
Yes.
Okay, now my v of x, this is simply going to be the natural log of 4x plus 3 times, and now I need the derivative of this over here. The derivative of this is simply 4 over 4x plus 3. So I've done my due diligence, that is the product rule. My final answer in this case is going to be negative 12x over 4x plus 3 minus 3 natural log of 4x plus 3. Okay, so just take a moment. I don't know if I'm going too fast or so slow. I don't hear much commentary, so I assume we're okay. But if you need a minute for that, that's cool. Let me know when. And I have a couple more for you. And this is a kind of math that eventually will stick once you practice it some more. Okay, I'll call this 5b. How's that? And I'll do it in let's do it in red. Just to differentiate the color. So for this one, I'm giving you the function where y equals negative 3x natural log, and let's use 5x plus 7. Find for me the first derivative.
So I think I got my answer.
Tell me.
I got negative 15x over 5x plus 7 minus 3 natural log 5x plus 7.
Yeah, that's
Minus
what
3 natural log of 5x plus 7. Yes, that is correct. Is that what everybody got so far?
That's what I got.
You want to
Like-
try another one, or are you going to move on? What do you think?
One more to come.
I can
One
do-
more? Let's
Yeah.
do one more. Why not? Why not? One more is always good. All right, so let's call this example 5C. And I'm going to ask you, if I give you a function, call it y equals negative 8x. This is product rule again, natural log of 7x plus 6. Can you get me the first derivative? Now, if it helps you, I'll shrink this down so you can see the first one I did with you and go from there.
Yeah, I have a possible answer here.
What do you think it is?
Negative 56x over 7x plus 6 minus 8, negative 8 natural log 5x plus 7.
So you have negative 56
Yeah, x.
over x over 7x plus 6
Yeah, minus
minus 8 natural log,
yeah, plus 5x.
7x,
5x plus 7.
7x plus 6, right?
Yeah, that's right. That was from the previous answer.
Yeah, no, I know. I figured you got the apples and oranges.
I'm an antsy guy.
I got you. I got you. All right. So I think you've nailed that one. I am confident. Let me give you this question. This one is a little funny. It's another product rule question. So this says S is equal to T to the 23rd power. Natural log of the absolute value of T. What do you think? Call it number 6. This is also product rule, believe it or not.
Is it T to the 22?
Keep going.
I thought it was T to the 22 because I thought it was T to the 23 over T, and that would make it T to the 22. That was my final answer.
Okay, well, so you have to go through the whole product rule thing. So I would begin with looking at this in terms of U of T and V of T. So if I'm looking at U of T, this is obviously T equal to T to the 23rd. And if I'm looking at the first derivative of this will end up being 23 T to the second 22nd power, correct? If I'm now looking at V of T is going to be equivalent to my natural log of the absolute value of T. My first derivative of the V of T, make sure that's a V, V of T is going to be equivalent to 1 over T. So if I'm implementing that power rule, this is going to end up being so this will be T to the 23rd times my 1 over T. Be careful with that because remember this is over 1. So this, your first impression of saying that that's t to the 22nd is not off, by the way. But this continues, there's more to this. When we add this, this becomes our natural log of t. And this is times our 23 t to the 22nd. So your answer here will be 23. That looks funny. That wrote very funny. I don't know what happened there. 23 t to the 22nd. And this is times the natural log of t. So you are correct here, but you need to remember there's more to this formula. So would you like to try one more of these?
Yeah.
Let's call it 6b. And I'm going to give you a function where s is equal to t to the third natural log of the absolute value of t. And remember, once you get the derivative, it's simply just a rate of change. It's like a slope. It's some y run over some x run. So what would be this first derivative?
Well, I think it's t squared plus parentheses 2t squared times the natural log of t.
So I'm saying it's t squared plus 3t squared times some natural log of the absolute value of t. That's what you said.
All right.
That's correct. And again, just simply follow the power rule, which is your you're looking at your u of t in this case. Your u of t times that v of t derivative plus the v of t times that derivative of u of t. And that's what you have going on there. It goes just back to the power rule. You just need to remember that you end up with 1 over t, which cancels you out. Okay, so that wasn't terrible. Let's take a look at a different concept. Same concept, but different process. So here I had given you a function where y equals the natural log of x plus 5, absolute value of x plus 5, to this x power. Can you find that derivative?
I find the derivative for this.
Well, I would say to you, think of chain rule where you would do 6 natural log of x plus 5 to the 5th, and this over the g of x, x plus 5. It's that simple. So if you notice, I multiplied by 6, I took away 1. Leave it alone, and you're simply, remember this is 1 over anyway, so that will simply end up being over the x plus 5. I could give you another example. Let's see how you do on this one. Call it 7b. I'll do it in red just as it differentiated. So this is y equals the natural log of x plus 2 to the 5th power. So what do you think this one is?
Would it be 5 times the natural log of the absolute value x plus 2 to the 4th power over x plus 2?
Rockstar. Excellent. Good job. Would you like to try one more? Or do you have it? I'm going to keep going then. I'm going to go to example 8 of the examples I chose for you guys. Just to practice this, I'm asking you here to differentiate. If I have a function, let's call it f of x, and let's call that absolute value of the natural log of 9x. So if you go back to what I shared with you originally, remember that the original function, the first derivative, is going to result in 1 over x. And so in this case, you end up with 1 over x times the natural log of 9x. And I actually forgot to mention that this is natural log times. That's why we end up with 1 over x times 1 over natural log of 9x. Let me give you another one since I messed that one up. Let's call this 8b. I'm giving you f of x is equal to the natural log of the absolute value of the natural log of 16x. Okay, and so re-express that using the logic I shared with you.
One over x times the natural log of 16x.
Yep. 1 over x, and then natural log of 16x. Pretty easy. Going once, going twice. Are you catching on to the patterns, or the more you practice this, the better off you'll be or feel. I'm trying to give you examples so you don't just have the note. Just note, someone just see what it looks like. Okay, let's look at number 9. At number 9, I'm gonna simply say if I have a y equal to some log of some number 17x, for example, this simply the first derivative is simply going to be, in this case, 1 over the log, in this case 10x. It's that simple. Doesn't matter what number I have in here, I can change this to anything I want. It's not going to make a difference. I can explain it this way. In this case, if let's say I hypothetically have y equals log of 12x, then I'm gonna think of this in terms of the derivative. So d over dx of some log base a of a g of x. Right? And then we also know that this becomes 1 over the natural log of that base times the first derivative of the g of x over g of x itself. So in our example, I'm talking about this one, this becomes 1 over natural log 10. This will be times 12 over 12x. And so that reduces to simply 1 over natural log base 10x. Is that easy enough to take in?
Yeah.
Awesome. I have a couple more examples, and then I'm going to go into trigonometry and trigonometry concepts. And so let's call this example 10. If I said to you, I have the log of the absolute value of 7 minus x, and I ask you to find the first derivative. So I want you to remember that I'm looking at this 7 minus x. And I'm thinking that the first derivative of the 7 minus x is simply going to be -1. The original g of x is exactly what you see, the 7 minus x. So my using this same philosophy that we would use, we would have -1 over the natural log of base 10 times the 7 minus x. So you can see they play a role. So this is your g of x, and this is your 7 minus x. And the log, which we assume is base 10, is always right here. Okay, I'm going to give you 2 more examples here just to kind of lead you into the last part. What if I said to you in question 11 or example 11 where y equals 11 to the power of x, and this is times the log of base 11x, and I'm trying to determine its first derivative. And so in this case, I want you to remember that you have a u of x, which in our case is the 11 to the x power. We have the first derivative of the u of x, which in our case is going to be 11 to the x power of natural log 11. Our v of x, we are going to refer to as the log base 11x. And our first derivative of that log is simply going to be 1 over natural log 11 of x over x. So if we use product rule, because this is technically a product, if you think of it that way, it's 11 to the power of x times log base 11x. So we're going to use power rule. We're going to end up with, in this case, 11 to the power of x. So as we're multiplying it times the first derivative right here, you're going to end up with natural log 11x as a function, because 11 to the x times that gives you that, plus the log base 11x times 11x natural log 11. all of this is your first derivative. Basically the product rule. Okay. I'm going to now skip over and go away from natural logs, and I want to go into trigonometric functions and the derivatives. So I'm going to leave this baby alone. Let's go to the next step. So this is all about basic trigonometry and their derivatives. So, for example, if I'm looking at derivatives of the 6 trigonometric functions. So if you recall, we have sine, cosine, tan. And so if we look at their derivatives, give me 1 second, I just lost my page. Where did I put the page? Okay, so the derivative of sine, we are looking at that as being simply cosine x. So if you have sine x, the derivative, this is the equivalent f of x. This would be the equivalent first derivative of each. So if I'm looking at cosine, its first derivative is negative sine x. And if I'm looking at tan x, its first derivative is secant squared x. So I have lots of examples where we're going to focus on that. And so let me go further from here. If we look at the derivative, so if I said to you, I have the derivative of cosine x, that derivative is the negative cosecant squared x. If I'm looking at the derivative of secant x, do you remember what these look like? It'll ring a bell once you see them. I can graph them quickly. We have secant x and tan x as the derivative of secant x. We look at the derivative of cosecant x. Its derivative is simply negative cosecant x cotan x. And so as I draw these questions and I use them with you in the examples, if you get stuck because you forget what we're looking at, just tell me and I'll go back and review this with you. Because I'm sure some of you have a little bit of
On the right column, is it COT?
yeah, cotan.
Okay.
Okay, so let me start you with some notes on this. Oh, like I said, I'll take my time, we'll do it together. And in the notes, which I have tons of, oh my God. I'm never gonna finish. You and I will be funsy friends for a long time. No kidding. So they begin with a little reminder for us. So they begin with the difference, the sum and difference quotient. Do you remember the sum and difference identities? I'll take that as a no. Or did you vaguely
Yeah, is
remember
that
these?
talking about like dividing versus minus and
Yeah,
plus?
this is just sum and difference. So this is just like, for example, the sign of some x plus y value and how that is distributed. Just remember that these are basically sine x cosine y plus cosine x sine y. So this is one of those trigonometry identities that we need to remember, or at least recall for a little bit. And if you have sine of x minus y, that's going to give you equal to sine x. cosine y minus the cosine x sine y. The cosine values, if you have cosine of x plus y, this is simply cosine x, cosine y, minus sine x, sine y. And if I have the cosine of x minus y, this is equivalent to cosine x, cosine y, plus sine x, sine y. So that is just a little bit of a recap. If you do also remember that if you have sine squared x plus cosine squared x, that this is equal to 1. I need you to remember this one because this one I saw came up in a couple of examples. And so that's one of those trig identities that we just need to remember. Going back to this is also something you need to remember. So these are kind of like, I don't want to say memorize, but if you just remember them, that'd be great. And same thing goes for the functions and the identity. All right, so let me get going. Yes.
On the functions part, is it sine x times cosine y?
Right.
Okay, that's what I'm really sure.
So say it again.
I just wanted to make sure.
Oh yeah, they're on multiplication at that point.
Okay, it's been years since I've had to remember
Oh.
any.
Yeah, I don't have an issue with that. Let me go here for a minute. I'm gonna pull up Desmos for a second. So if we look up Desmos, if you can see my chart, you can see that I'm gonna graph sine x, for example. Remember sine x?
You mean the shape of the function?
Yeah, you remember it goes through 0, 0, and it goes as high as 1 and as low as 1, -1. Do you remember that? Are you seeing my screen?
No,
You're not seeing my screen?
no, I see the group of students.
Okay, hang on. I should be sharing my screen.
We're good.
Were you seeing everything before this? I assume yes?
Yeah, yeah, all the notes. Yeah, now we're
Okay.
good.
Because I would cry right now in front of you with no shame. So that's sine x. You remember those little basics, like it goes through 0, 0, and it goes as high as 1 at pi over 2, which is 90 degrees. You remember that?
Oh, I do remember this. Yes.
Okay, it goes as low as 3 pi over 2 at 3/4, and
Mhm.
it literally ends at 2 pi. So everything that's highlighted right now is just one cycle, right? And that's just sine x. Cosine x is very similar. So if I look at cosine x, the only difference is it goes through where y is 0, 1, and it does go as low as, that's all of one cycle of cosine. Okay, and then tan. Tan is our weirdo. I call tan the weirdo because tan is the only one that does that up and down increments of pi over 2. So like it has its knees at pi over 2, it keeps turning. And then these are the fun ones, the secant and cosecant. So let's look at cosecant first. So here's cosecant x. You remember this one? where it has these basic values that are going up and down. If you notice, so at pi over 2, then it hops over here to 3 pi over 2. So at pi, there's nothing, there's a straight line. If I look at secant x, same difference. Remember that it goes with cosine, so obviously it's hitting the 0, 0, 1 area. And so once again, on this one, if you look at the values, that one goes through pi. And so there are areas where it's not differentiable because you have a vertical line. And then cotan. Basically, it's cosine inverse. Same thing, it has the same cut or turn. Okay, so that's just a quick reminder of what they look like and why we're gonna differentiate them the way we are. So let me start, and don't get nervous. Just ask me questions. If it's something doesn't come to you right away, let me know what it is. And I'll bring you back to the reality of why it is what it is. So in example 1, they're starting with the fact that when you look at the limit as x approaches 0, if you're given the sine x over x, and that limit is 1, and you saw that why it is. When you look at the diagram, it goes through, so here's a quick little model. Here's 0, 0, goes through here and goes up and down like just like this, right? It caps at 1. It also caps at -1. We don't really talk about it, but when it gets to 0, we're looking at 1. And so we're also looking at example 1. In example 1, we're looking at the limit of h as it approaches 0. And this is if I have cosine h minus 1 over h. And so the rule of thumb here would be I would multiply both sides, top and bottom, by its conjugate. So if I multiply this cosine h minus 1 times h, I'm going to multiply it by its conjugate, cosine h plus 1 over cosine h plus 1. All right. So having done that, this becomes the limit as h approaches 0 for cosine squared h minus 1 over h times cosine h plus 1. Now, remember how I said to you, don't forget sine squared x plus cosine squared x equals 1? This simplifies to be negative of sine squared h over, obviously, the h cosine h plus 1. If you use your calculators, you also will note a couple of things about sine at 1. So if I simplify this, the limit as h approaches 0 ends up being negative sine h times sine h again over h times 1 over cosine h plus 1. Using your calculators, if you look at the value as h approaches 0, this gives you negative of sine of 0. Negative sine 0 becomes 0. This is sine 0 over 0, which technically becomes 1. And this becomes 1 over. I'm losing my space here. Hold on a second. Let's go this way. So this is 0 times 1 times 1 over 1 plus 1. And the value obviously is 0 because you're multiplying by 0 anyway. So we know that the cosine of h minus 1 over h as it approaches 0 is 0. So basically all of that is 0 anyway. If we look at this first derivative function, which is basically as the limit of h approaching 0, just take this in for a minute. I know some of it may not click right away, but it will as I continue talking. So we're looking at the first derivative, right? The difference quotient. If we do this and we solve for this in terms of a function, let's say the f of x function is equal to our sine x function. Okay, so we use this as an example. That first derivative function becomes the limit as h approaches 0 of sine of x plus h minus the sine of x and all of this over h. If I continue to expand this, the limit as h approaches 0 so the limit as h approaches 0, in this case, as I expand it, becomes sine x cosine h plus cosine h times, cosine x times sine h. So sine x cosine h plus cosine x sine h minus sine h again, or sine x again, we're just doing this over h. Let's rearrange some terms. So you end up with sine x times cosine h minus sine x again. All of this minus cosine x times sine h and all of this over h. This ends up becoming sine x times cosine h minus 1 plus cosine x sine h and all over h. And so as the limit as h approaches 0, we end up with basically the limit as h approaches 0 ends up being sine x times your cosine of h minus 1 over h plus your limit as h approaches 0. We're splitting the equation basically. This will become cosine x, and this becomes sine h over h. You end up with sine x times 0, and this becomes plus cosine x times 1, which results in cosine x. So therefore you just proved using all of this, that the derivative, the d of x, given the function sine x, is simply cosine x. Okay, so that's just a proof. It's just proving to you how we get there. But more importantly, how do you use it? So let's do a few examples. Let's look at example 2, for example. If I give you a function where y equals, and I say to you sine of 6x, and I want to know the first derivative, it's as simple as 6 times cosine of 6x. Again, we take the derivative of the cosine, or of the sine. We take the derivative of the 6x. So this becomes basically the cosine of 6x times 6, but instead we put this up front, which is why we have 6 cosine 6x. See if I have another example I can throw your way. Okay, so let's say I give you a function. I say to you, I've got some function y equals some fraction 3/5, and I say to you that's times cosine of 15x, finding its first derivative. Can you agree that it would be -9 sine of 15x? Because remember, you're going to take this number, whatever this number is, you're going to multiply it out here. In this case, because you have a 3/5, 5 goes into 15 3 times, so 3 times 3 is 9. The derivative of cosine is -9, so hence -9 sine of the same 15x again. Okay, let's try another one. What if I said to you, I have another equation, let's call it f of x. And that equation is 1/5 cosine 15x. Can you find for me its derivative?
Got 3 sine 15x.
Yeah, so this is going to be negative, right? -3. Because sine is negative sine. Negative sine times 3. So 5 goes into 15 3 times. 3 times 1 is 3. But it's negative sine, and then obviously the 15x stays. Because cosine, if cosine is the function, this is your f of x, is cosine x, right? The first derivative of x, of cosine, is going to be negative sine of x. Okay? Okay. Let me switch pages real quick. Okay, I know it's a little bit of I've run over a little bit, so if you can stay, please stay if you want to. If you don't want to, I'm gonna record this so you just continue listening from 7:31 on. If you have a class, obviously please go. If you want to stay with me, I'm gonna continue until I finish the next 5 examples, and we should be good after that. Okay. So in this, as I continue, let's look at the derivative. So d of x of the function of cosine, as we've mentioned, that is negative sine of x. So an example of how we would use that would be something like if I ask you, what is the derivative of the cosine? And I give you 3x, what would be your answer? I think we already did this one. This was going to be -3 sine, and then the function 3x. Even further, let me give you this example. What if I gave you a function and I say to you, I have some f of x function, and that f of x function is cosine to the 4th x, and I want to know its derivative. And so in that case, I need to employ the power rule, so this, or the chain rule, so this become 4 cosine to the power 3x, right? And then times the derivative of cosine, which is negative sine x. My final answer, if I were to put this all together, would be -4 sine x cosine to the power 3x. Okay, so you need to take a few steps on that one. Now, the one that's going to throw you for a little bit of a loop is example 5. Example 5 are the derivatives of tan and cotan. So let's look at some examples of that. If I said to you, I've got a derivative, and that is equal to tan of 9x, find the first derivative. So you need to remember the derivative of tan is secant squared x. So this is going to become 9 secant squared x, 9x, I'm sorry, squared 9x. All right. Let's look at a cotan. We haven't seen a cotan yet. Example, call it 5b. If I said to you, I have a function, f of x, and that is cotan power 6 to the 6x. And I said to you, find its derivative. So its derivative, if you recall, this is going to be negative, because it's negative cosecant squared. So it's -6 cotan 5 secant, oh, cosecant, sorry, cosecant squared x. So cotan to the power of 5x cosecant squared x. And so once again, go back to your rules. I believe I mentioned that at that point, these are going to be negative. So this would lead me to bring it to this rule. For the derivative of tan x, d of x of tan x is equivalent to secant squared x. The derivative of cotan x, that is equal to the negative cosecant squared x. That's why this one ended up being negative. Okay, I'm going to follow you with these two last examples, where I have d of x is equal to secant x. And this one is long. This one is secant x tan x as a derivative. and the derivative of cosecant x, well, this is going to give you negative cosecant x cotan x. So let's do a couple of these examples and I'll finish for tonight. So an example of that would be if I gave you a derivative, find a derivative of x squared secant x. You're going to need to use a product rule. Remember, you have x squared and you have secant x. So split it up. This is one function and the other one is the x squared function. So think of that as u of x. So if I use product rule in one foul swoop, I'm going to set it up with x squared, the derivative of secant x, which is times secant x tan x. Okay, so that's the first part. The other part would be plus the derivative of the u of x, so that would be 2x times, and then this would be just the v of x, which is secant, the original secant x. So that's all I would need to do for that one, because that's pretty straightforward. So that's that example. I have the derivative of cosecant e to the 2x. Once again, I caution you, these are two separate functions. I would again use product rule. So if I did that, remember, go back to your basics here. So I'm going to start with negative cosecant e to the 2x cotan e to the 2x. And this is going to be times the derivative of the e to the 2x. So this is times 2e to the 2x. And if I simplify this, this will be simply negative 2e to the 2x cosecant e to the 2x cotan e to the 2x. All right. Anything else that's relative or no, not really. All right, I think I'm good for today. Let me stop the recording here so I don't mess this up. So stop recording.